So let's jump into today's topic. We're going to be talking about measurement error. I don't have that many slides on measurement error, so we should be able to get through it, discuss it, and get you all a chance to begin looking through the topics for today. I have a quote here. "The grandest discoveries of science have been but the rewards of accurate measurement and patient, long-continued labor in the minute shifting of numerical results." I like that quote a lot. It's by a gentleman who has been given the nickname of Lord Kelvin. Kelvin is a temperature scale that we will learn about today. And so this is somebody who knows very much about measurements and where we use them. Speaking as somebody who was an engineer, I also can say that measurements were my entire job. That the reason I think measurements are so worth our time is because it is impossible to optimize what you do not measure. You cannot improve things if you don't have the ability to measure them. So that's really what this is coming down to, is that we want to be able to measure things so that we can improve, we can change, and we can prove that change to other people. So let's go ahead and jump in a little bit. Here we are. So in this section, we're going to learn how to work with units. Remember, we worked with units before. Specifically, we were talking about unit conversions. How do I convert between one type of unit and another as if it's a change in perspective, right? As if somebody else in the world speaks about distance in terms of meters, but I grew up in my family speaking about distance in terms of feet and miles. So we know this way of being able to relate to different cultures that are all trying to describe the world around us. Many of these measurements can be done indirectly, or they can be approximated, right? We can all, for example, guesstimate each other's height based on our own height, right? This happens quite often. Or I could estimate that my door frame is probably about 7 feet tall, 8 feet tall, because I know that I am about 6 feet tall. So we can use these references. All measurements include a certain level of uncertainty. And this is an important thing. I remember I was working with some teachers over the summer, a couple summers ago. And one of the challenges we gave to these math teachers is we brought them into a parking lot and we asked them to figure out how tall the lamp posts are. And I thought this was a very interesting exercise because, first of all, there is no one way to do it. You could try to look at its shadow and then figure out how its shadow determines its height. You could take a picture and then hold a ruler up to the picture and then kind of scale it. You could put somebody next to the lamppost and then guess how many people stacked on each other's shoulders would fit the lamppost. All of these were really good techniques. But I remember at the end of the class, people asked the professor leading the exercise, they asked, "So what is the actual height?" And this math professor said, "I'm sorry, I didn't, actually go out and measure it exactly. I don't have the exact number." And everybody got all upset. They, "Oh, why? He doesn't have the right answer. That means that we can't know the right answer." And I had to stop everybody. I had to remind them that there aren't right answers for those questions. For example, how tall am I? I am not 6'2". Even though on all of my doctor's records it would say I'm 6'2", because I actually could be a little bit under 6'2", a little bit over 6'2". It just means I'm just that's the best number, but that's not the number. And so in the same way, if we go out and we measure a lamppost, no matter what ruler we use, we will have to do some rounding. We will have to do a little guessing. And an interesting example of this happens if you look in encyclopedias across the years and you ask, how tall is Mount Everest? Many, many times you will see that number change. And it's not changing because the mountain is changing. It's changing because we are getting better at measuring. And that when we get better at measuring, we change the number. So we won't ever know the correct number. We will just always know better numbers. And that's something I think that's really, really worthwhile, because people are always looking for the right answer in science. And I think it's worth remembering that there's not always a right answer, there's just always better answers and better justification. So let's talk a little bit about that measurement error. We have sources of error. We have those that the humans introduce. Excuse me. These would be errors that result from making mistakes, right? Like maybe I misread, or I don't set up the instrument correctly. Maybe I communicated incorrectly. So we have human errors. We also have measurement errors. Measurement errors are just limitations. They're how, like, for example, if I wanted to know how big an atom is, I would not be able to use the ruler that sits on my desk. That would be too big. I would not be able to get an accurate number. And in the same way, if I wanted to figure out the distance between my house and my parents' house, if I used a 1 foot long ruler, that would not be the appropriate instrument. It would be imprecise. I would want to use something like a GPS, or I would want to drive my car and then look at what the odometer carries. So we have what's inherent to the measurements, and then we have what we introduce and can fix. So if we can change it, if we can make it better without changing the instrument, then it's human error. If it doesn't matter how good a job we do, we will never be able to get a perfect answer with the tools in front of us, then it's a measurement error. We also have random error. Random error is error that's due to just natural fluctuations. Like, for example, if you go and you, I like to make French press coffee in the morning, right? Because I'm fancy like that. So I make French press coffee in the morning, and I have found that if I make the water 185 degrees Fahrenheit, that's the best temperature for coffee water. But that depends on how big of a container I have. It depends if somebody sneezes on the water and blows some of the steam away, right? I can't always make things perfect because the world gets in the way. That's going to be random error. Systematic error is going to be error that tends to where we have a consistent overestimation or an underestimation, right? So maybe we have somebody who like really, really, really wants to be tall, and so they kind of round their height up a little bit. I have been guilty of this. I've called myself 6'3" when in truth I was 6'2.5", right? So we could absolutely have just sort of this issue of saying I'm doing it a little bit over because I have a desire. Or maybe on the production line, maybe we're trying to cut corners, right? We're trying to give a little bit less than a certain commodity, and we hold some back because we want to increase our bottom line. Excuse me. So with sufficient care, human error and systematic error, we can control these, right? We can put in people to observe, we can have supervisors, we can make sure that we're doing the best we can with trying to remove these two errors. But if the measurement error, which again comes from the tool, and random error, which just comes from the fact that life is not always going to sit still for us, get in the way, then we're always going to have a little error. And that's okay, that happens. That's just the way the world works. Now, the other terminology I want to introduce you to, just so that it helps out with our dialogue, is the difference between accuracy and precision. Accuracy, this is referring to how close a measured value is to its true value. So accuracy is how close to truth we are. Precision refers to the level of detail or the refinement of a measure. So in other words, it's talking about, can I consistently get similar readings? So for example, maybe my oven runs cold, but every time I set it at 300 degrees, it always ends up turning out 280 degrees. That's definitely wrong, but I can control for that by just setting my oven at 320 degrees, and then that will pull up what it actually gives me to 300. So we have this idea of saying precision is the ability for me to trust that it will be consistent. Accuracy is whether or not it gets me close to the truth. I like to look at these through a picture. I think that a picture helps to compare. So accurate and precise is definitely what we want. If we're pretending like we're throwing darts at a dartboard, we want to hit exactly where we're aiming, and we want everything to get there. If I am not accurate, but I'm precise, that means that I can trust that I am always going to hit somewhere else, and so I can always make just a correction. I can always just try to adjust for it, and that will get me just as perfect. If I'm accurate but I'm not precise, that means that I'm trending towards truth. It just means that I'm not always close to it. So again, we've got this idea of accuracy being the close and precision being the grouping. How consistent am I? And then obviously there will be some instances in which you are neither accurate towards the bullseye, nor are you close to any other attempt, any other measurement you make. Let me pause here for a moment. I just want to check in. Does anybody have any questions about what it means to be accurate and precise, not accurate and precise, any other combination, or how error plays in this story? Yeah, no, good. So let's do an example. For example, let's imagine a scale, like a scale at the grocery store where you're going to measure some fruit, right? If I had an accurate scale, then that means if I put 3 pounds of apples on it, it will tell me pretty close to 3. That's what the scale will tell me. It might say I'm a little bit over, it might say I'm a little under, and depending on how far away from 3, that would be how good or bad an accuracy I have. So if I'm close to 3, that's going to be accurate. If I'm far away from 3, that's not accurate. So I want it to be, so accuracy is the truth. Precision is talking about what if I have a scale where I put 3 pounds of fruit on it, and it always tells me 4 pounds. That's not awesome, but at least if I put something on the scale and it tells me 4, I know that it's actually 3. So precision is the ability to trust that it will be consistent. It might be consistently wrong, but it'll be wrong in the same way. And so I can still use that data. I just need to make an adjustment. Does that help out? Okay, excellent. Good. Obviously, we want both, because if I just simply say that most of the time it's near 3, that's not great. If I say that most of the time it's very close, it's always off by 1, that's also not great. I want it to be off by 0 and close. So it's that idea of saying I want it to be close, accurate, or I want it to be off by 0, accurate, and reliable, precise. So note, for example, that we will always be limited by a certain level of precision, right? So for example, if we measure a length with a tape measure and we mark off every 1/8 of an inch, then all of our measurements will be accurate only to 1/8 of an inch. That means that if I want to measure anything smaller than that, I will not be able to do it well. So I might be decently accurate, or excuse me, decently precise, because I will always be able to use my eyes to find a number, but I'm always going to be inaccurate because I have to rely on the ruler, and the ruler will always be a little wrong. Okay? It's difficult. These words do kind of stumble over each other. So it's a matter of saying, can I get consistent data? And can that data be trusted as being close to the truth?